it's very easy to see that 2, 4, 1, but this matrix times 2, 4, 1 doesn't map to 0. Without doing the calculation, how do you know that?
Because the number times itself, unless there's zeros, it's not going to be 0.
Why would, what times itself?
Anything times itself unless it's
Oh,
0.
anything, no, I can't talk about anything. Be more specific, any what?
Any number.
Any number times itself? Doesn't equal 0?
Unless
the
it's
number's
0.
0. Okay, that's a good start. But we're not talking about a number times itself. What are we talking about?
An equation times the same equation as that equation squared.
I think what we're talking about is a row of numbers times a column of the same numbers. Okay? So you want to be specific about it. The essence of what you said is good. I'm just trying to start training you to be really specific, okay? Since 2, 4, 1 is a row of numbers, not all 0. Okay? Haven't mentioned the word transpose. So it gives us a sum of squares of numbers at least one being non-zero, right? Okay? Now for 2, 4, 1, 2, 4, 1, of course we can do it, we get 21, okay? When we multiply this by this, well, already the result isn't the 0 vector, right? Okay? And we can do the same thing for this second row. Okay? So we can say then, so two, 4, 1 isn't in the null space. Similar argument. Neither is 1, -3, 2. Okay? Now, if I had more terminology, I'd say the transpose of the first row is not in the null space. Transpose just means you take your rows and make them into columns, and your columns and make them into rows. Okay, so you do the transpose of the matrix, just kind of turn it around a little bit. Okay, so you have column 2, 4, 1, column 1, negative 3, 2. Okay. So that's the word transpose. Pretty easy idea, but it has really neat ramifications, especially if you have a space that has an eigenvector basis. Okay, but that's much later. Okay, since you know what eigenvectors are, I mentioned it. Okay, similar argument then, neither is this. And since the matrix exists in this form with an identity matrix here, neither vector is a multiple of the other. Okay. Also, any set of multiples, any sum of multiples of these vectors can't be in the null space. Okay? I want to see if we can prove that. Okay, just like the homework assignment I gave you, prove these things. Prove everything I said last time or whatever it was. Okay? We'll give an example. I think I asked for last time, give an example of everything which you did. Then I asked for proof. Incidentally, I've got that to give back to you. Okay. Make sense? They might not see how to prove it. Play around with it, maybe you will. If not, I'll show you. Okay? And the set playing a little set notation on you. This says the set of all sums of multiples, C1 times this plus C2 times this. This line means such that C1 and C2 are both real numbers. In other words, it just says just take all possible sums of multiples of these numbers by real numbers, or vectors by real numbers. It's a plane in R3. That plane is perpendicular to the line of the null space. Well, there's something you need to know about perpendicular. So I might just assert it because it's really easy to calculate. I'm not going to prove it because it requires some trigonometry. And can't assume that everybody knows the trigonometry. Okay? I think half the class does. Half the
I
class
don't make
probably
the
hasn't had it for at
this.
least a decade, if at that point, but we'll understand it just fine when we ask them to learn just a little bit of trigonometry so you can follow some of this stuff. Okay? Okay, so perpendicular. Okay, before I go on, I just want to draw a picture. Then I'll show you how we prove that it's perpendicular. It's so simple you can't believe it. But why it works that way. Just high school trick. It's a trick. Okay, so we have this picture. Okay, I'm going to draw this picture. Here we've got R3. And here we've got R2. We've got our transformation defined by the matrix A. Okay? So what we have is, I'm going to represent it like this, even though this looks like two planes. This is going to be the null space. It's really a line, but we're going to use the same picture if we have R17 and R34, okay? Or R58 and R46, okay? The picture's going to look the same because we can't picture a 14-dimensional subspace of R46, okay? So we just do them by rectangles that are aligned like this to kind of indicate that they're perpendicular to each other. I mean, they really aren't perpendicular the way they're drawn, but that's how we're going to kind of indicate orthogonal or perpendicular subspaces. So this is really a line, okay? And you do have a right angle here and a right angle here, so they're kind of like at right angles. But you can't picture two planes at right angles unless you do a three-dimensional sketch. And that gets messy. And then also, they're not only at right angles, but the only place they intersect is at the zero vector. That's impossible to draw in 3 dimensions. If I draw this as a line, it's not that hard. You know, just draw a plane and then draw a line that looks like this perpendicular. Okay, so anyhow, we have that. The null space, it's really a line in this case. In the general case, we got Rn to Rm. It's not a line. Not often a line. Okay? And then this is the space of all vectors that don't go to 0. Okay? Now there's a name for that, but I'm just going to call it the space of all vectors what ain't null That means all the vectors that don't go to 0, right? And there's no overlap except that a space of vectors always has to include the 0 vector, which does go to 0. Okay? So that vector is the 0 vector just like right here where these things intersect. Okay? And they do both contain the 0 vector, even though so it's a space of all vectors that aren't null plus the 0 vector. It wouldn't be a space if it didn't have a 0 vector. Vector space has to contain the 0 vector. And this is a vector space within a vector space. We'll talk about that, properties and so forth. Not difficult. Okay, so in this transformation, this space here maps to all of R2. And this space here maps just to the 0 vector. Okay? That makes sense? Also, if this space isn't empty, there are vectors in the space that aren't in either of these. Because if you've got a plane and you've got a line, all the vectors from the origin out to points of the plane, all the vectors parallel to the line, then you can add some of these to some of these, and you're not in that plane anymore. And you're not on that line anymore. Okay? So you have vectors up here. No place to label them because I didn't anticipate. Okay? And there's something I've stated incorrectly here, because any vector here would not be null. Okay? So, I labeled this wrong. I said it was kind of ignorant. Fortunately, I said more and showed myself why it was ignorant. So let me fix my ignorance here. Okay? I said this thing had a name, and I should have used the name, which I know perfectly well. Because if I'd used the name, I wouldn't have written what I did. Okay? So this is called the row space. Okay? Sum of multiples of the rows of A. That's what forms a plane. Okay? And then I said sum of vectors in the plane and vectors on the line. Okay? And that's okay because that terminology is implicit, but it's going to be better. If I say vectors, which are vector sums of vectors in the row space, and in the null space. Okay? And there's a name for that. It's called a direct sum, but I'm not going to use that terminology now. We'll see it when we write down the definition, and you see it in your book, and you have it where you can read it. Okay, but the concept is, again, this is R3. There's a line through the origin. Any vector from the origin to a point of that line is going to map to the zero vector, and we figured that out. Evan did it right. Multiples of that, 11, 3, 2 vector. One of those is negative. What is it? Yeah, negative 11, 3, 2. Okay? 3, 10. 10. So that's this. So these are the vectors here. Now you got a plane that are claimed as perpendicular. I'll show you how simple it is to do that once you understand what a dot product is. Okay? This plane is the plane you get when you do sums of multiples of the rows. We call that a linear combination of the rows. And I'm saying sums of multiples of rows because you'll see the term linear combination and you'll already know what it means. You'll have a name to put on it. Okay? But you have also a statement that says what it means. Sum of multiples of it. And you got two vectors here. Let's see, one of them is in this direction. One of them is in 1, negative 3, 2. These two directions, they form a plane like this. The negative 11, 3, 1 vector goes back this way, over this way, and up once it's in this direction. And it's perpendicular to this plane. Okay? And the way I gestured that doesn't make sense, but you have to draw it out. You get it. Okay? And any vector in space, then, can be obtained by going to the appropriate point of this plane and taking that vector from the origin to that point, and then taking a vector along that line. Takes you up to wherever you want to be. Takes you to the vector that you're trying to make. Does that halfway make sense?
Sounds like you just created a wormhole through space.
Nah, nothing like it. I've been through lots of wormholes. They don't act like that at all. Okay, now, okay. This is part of a really big, important picture that we kind of close out the course with. That was a picture of this space over here also. Okay? You take, it's not good to illustrate that with R2 and R3 because one of the spaces is just all of R2, the other is just zero vector. You take what's called the row space and the transpose, okay, and another space, and you put them together. So you got a picture over here that looks like this, and then you prove some really neat stuff. Pretty abstract, though, so we're going to take a while to build up to that. But I think you can handle this much. The last thing, I'll go ahead, because it's really simple, although we're not going to prove anything with it for a while. Because it requires the trig.
I never took trigonometry.
There isn't that much trig in this course, but proving that this. Okay, so I'm going to take the vector. I remember what it was. It was -11, 3, 10. Okay? And I want to do the dot product of that vector with the vector 2, 4, 1. Okay? Now this is called a dot product, and it's so simple that you wonder why we even do it. It's basically just what you would do if you made one of these a row and multiplied it by the other one as a column. Okay? So I can actually do that. Okay? This is a vector, we're dotting it with this vector. Okay, so dot product. Okay, this vector is going to be our V1. This vector is going to be our V2. Well, the dot product would just be take either vector and make it it's commutative. So it doesn't matter what order the vectors are in. If you reverse the order, it's going to be the same, and that should be obvious. You just take one vector and make a row out of it, multiply it by the column of the other. What do you get? Figure it out. Get it?
No, I'm doing
Are you
math.
still copying stuff down? You can see it. This times this is -22, this times this is 12, this times this is 10, they add up to 0.
Couldn't we have just multiplied straight across at that point?
Huh?
Couldn't we have just multiplied straight across at that
Yeah,
point?
you can define it as this times this, plus this times this, plus this times this.
Oh, I was going to do that.
But it's
first.
easier for me to define it as what you get if you do a row times a column. It takes less writing.
Okay.
And you can see how your book defines it, but it's 0. Okay? And -11, 3, 10, dotted with 1, -3, 2, equals 0. Okay? Well, in Euclidean space, that's just your usual R2 or R3 or Rn, whatever. But it's got a metric on it and stuff. But in Euclidean space, vectors are perpendicular if and only if and I should probably qualify it, non-zero vectors are perpendicular if and only if their dot product is 0. Now I'll ask you to prove something very simple, that if you do the -11, 3, 10 vector dotted with C1 times this plus C2 times this, you still get 0. Which means that every vector in the line that defines the null space of this particular transformation, okay? It's perpendicular to any vector in that plane, the row space that consists of the vectors that don't map to 0, okay? It's really, well, I'm not quite stating that right, but you get the idea. And then you prove that that's going to be the case no matter what your transformation is. That your null space is always perpendicular to the row space. See, so I can say the dot product of any vector that maps to 0 and any vector which corresponds to a sum of rows of the representative matrix is 0. Okay? There are a few little gaps in what I said, things that need to be proved. But once you know that, you know about half the course. It's a powerful tool. Okay? So, that's a dot product, very simple. Okay? Another thing I'll say is, the polynomial, the space of polynomials. Enter the space, a space of matrices. Things that you did some proofs on for last time, which all look pretty good. At least you did examples of them. Okay? And I think you also did some proofs. I'll get those back to you.